Many number patterns found in nature and used in business can be modeled by sequences, which are lists of numbers. Some sequences are classified by the method used to predict the next term from the previous terms. When the terms of a sequence are added, a series is formed. This video introduces the basic concepts of sequences and series. You are in Mathematics of Engineering. What is a sequence? It is a set of numbers which are written in some particular order. For example, take the numbers 3, 6, 9, 12, 15, 18, and so on. A series, on the other hand, is something we obtain from the sequence by adding all the terms together. With the previous sequence of numbers, we can obtain the series as 3 plus 6 plus 9 plus 12 plus 15 plus 18, and so on. By merely looking at the numbers, a sequence will have its elements separated by a comma, while a series will connect each element with a plus sign. There are two general classifications of sequences. A finite sequence can be specified by a complete list of its elements. In the following example, the last term is 18, implying that there are only 6 elements in the complete sequence. On the other hand, an infinite sequence can be specified by an incomplete list of its elements. It has an infinite number of terms, and in listing the terms, we use a set of 3 dots after the last term in the list to indicate that it has no end. Let's dissect the different parts of sequences. Suppose we have a sequence. The outputs or the values themselves are denoted as A with a subscript like A sub 1 is 3 and A sub 2 is 6, but such subscript are identified as the order of elements in the sequence, so the n of 3 is 1 and 18 is 6. In here, the A's are called terms and the n's are index or indices, and the first element is called initial index. There are 5 different families of sequences, the first 2 of which we are going to discuss further in the succeeding videos. The first family is arithmetic sequence, which is also called arithmetic progression and is denoted by a P. It is a sequence where each new term after the first is obtained by adding a constant d called the common difference. In our example, by checking the jump of 2 succeeding terms, like 3 to 6 is positive 3, which is the same with 15 to 18, a fixed quantity is added to reach the succeeding term. A geometric progression, or GP, is a sequence where each new term after the first is obtained by multiplying the preceding term by a constant r, called the common ratio. Suppose we have the sequence. The pattern of arriving to the next term is done by multiplying the previous, like 10 to 30, by multiplying by 3, and the same thing between 810 to 2430. The sequence of triangular numbers, or Tn, is a sequence of integers counting the number of dots in increasingly large equilateral triangles built from dots. The term Tn is the number of dots in a triangle with n dots to a side. There are a couple of ways of making this discussion more precise. Given an equilateral triangle with n dots to a side, how many more dots do you need to build the equilateral triangle with n plus 1 dots to a side? All you need to do to transform the smaller triangle to the larger triangle is an additional row of n plus 1 dots placed along any side. In formula, you can use the recursive formula as shown. By recursive, we mean the procedure will arrive at the value of each term and it will be in a sequence or step-by-step process. But the other way to computing Tn, indeed, you may use the explicit formula which is also shown. The famous Fibonacci numbers are defined recursively, starting with 0 and 1 and the rule that f sub n is equal to f sub n less 1 plus f sub n less 2. We can restate this formula in words instead of symbols. Stated in words, each term is the sum of the previous two terms, so the sequence of Fibonacci numbers is shown as follows. Here is a diabolical sequence known as Collat sequence. Subsequent terms are defined using the rule as shown, with the condition to use the first pattern when the term is even and use the second pattern when it is odd. If we start our sequence with a1 is equal to 6, 6 being an even number will adopt the first pattern for the succeeding term, which gives 3, and since 3 is an odd number, use the second term. Keep on writing the numbers until such point where the numbers will repeat from 4, 2, and 1. What if you are going to start with another number such as 25? Keeping up with the terms, the sequence will still end up with 4, 2, 1 loop because of Collat's conjecture. Nobody has found a value which doesn't return to 1. But for all anybody knows, there might be a very large initial value which doesn't really return to 1. Nobody knows either way. It is an unsolved mystery in mathematics.